So I don't know how many of you guys have been watching any of the videos, but I worked with a couple of students during office hours, and I thought it would be easier just to make you guys a review video. So this is an equation sheet from exam number 3, which will be next Tuesday, not this week. I can't even spell, exam number 3. And it covers chapter 4 and chapter 5. Chapter 4 is normal stress. Chapter 5 is shear stress from torsion. So chapter 5 is going to deal with torques, and chapter 4 is basically like our rubber band where we are applying either tension or compression. So that's where we are at this point. So we need to be able to recognize if we're looking at a normal force, normal stress situation or a torsion torque situation. So again, if I have a beam that's loaded and I cut it and I want to see internally what's going on, I could have a normal force, I could have torsion, I could have beam shear, and I could have a bending moment. And we have already gone through the exercise of working through our normal stress. And I don't know why it's kind of blurry. Maybe that'll help. And then we spent some time looking at torsion. Okay. Currently, we are working on normal stress due to bending, and those videos will be coming next. But right now, I just wanted to review. So we need to remember, again, we have normal stress from a normal force, and that gives us a stress of N over A, or P over A, or tension over A, or compression over A, whatever you want to call it. Okay. Then we have torsion, which is a twisting, like wringing out a wash rag or pulling paper towels off of a paper towel holder, twisting about itself. You're usually going to see this in some sort of like shafts that are spinning. And so it has a torque. So we have to remember that our shear stress is T rho over J, or our maximum is at TC over J. Okay. So looking at this equation sheet, I need to be able to distinguish as a student what it is I'm looking at. And I'm going to look right here first. Okay. This is normal stress. You need to remember that sigma means normal. This is, I have a normal force, or we could call it P. Okay. It is going to cause elongation, and I'll have a delta, or I have a normal force. Again, we have force P, and this time we have compression, negative delta. So this would be a negative P, positive P, negative delta, positive delta. So what is P? P is that internal force that I find that is perpendicular to my cross section. It is caused by that normal force. It is an axial load. So axial, however you want to look at it, normal force. Okay, and the stress that results is just that force over our cross-sectional area. And we need to remember it's the original cross-sectional area. You know, as we pull on or push on, we're also changing that cross-sectional area, but hopefully we're in the yielding zone of our material behavior. So we just are going to use that original cross-section. Okay, this is just force and geometry, internal force and cross-sectional geometry. Now, when I pull on a rubber band, I do see that I have deformation. So we are going from normal stress, which is just P over A. This is the function of the load that's being applied and the area. And we know that we're going to have some strain, some deformation, and that is a function of our modulus of elasticity. And if you all remember, I can have a stress strain diagram, and we usually have an elastic region, a very long yielding, kind of come back up, have an ultimate, and this is our yield stress. It's where we have this linear behavior between stress and strain. As I pull on my rubber band within that elastic region, I will have a lengthening, and when I let go of that rubber band, it will go back to its original shape, and I don't have any permanent deformation. So our assumption with all of these, okay, equations is that we are in the elastic region. So material behavior, modulus of elasticity, results in strain. Strain is length final minus length initial over length initial, which is our delta over length initial. That's where this equation comes from. It is taking P over A, which is my normal stress, and it's taking my modulus of elasticity, and my strain is change in length over length. We can rewrite that. Delta equals PL over AE. Okay, so PL over AE. This is where we have a very specific force through the segment. This would be if we have a variable force, so maybe it's increasing along the length, or we have a variable area, maybe it is being reduced in area, it's like looking like an ice cream cone, okay, as we go through. E, we have one material, okay, so that's the difference in these two. We can also have a change in length due to temperature loading. Alpha, delta T, L. So the length of the segment, the change in temperature of the system, and our thermal expansion coefficient. So you need to be able to recognize from the materials that you were given, either from the exam or in the back of the book, that this is E. It has to do with normal stress, okay? This is the yield stress. That is where I go out of the elastic region into yielding, okay? This is also related to normal stress because it's our coefficient of thermal expansion, and it will cause a change in length just like a load will, okay? Normal stress, normal stress, normal stress, normal stress, normal stress, normal stress. If you call anything that's a P over A, this normal force, if you call it torsion, partial credit is pretty much gone. You have to understand the difference between normal stress. Normal stress is causing a change in length. It's tension and compression, okay? Then we have this section. This is shear. Tau is always shear. Shear is that skewing. We originally looked at a block that maybe we applied a load to, and we got this gamma, our shear strain. If I were to look at a shaft that is spinning and I put a square on the outside, as I apply that torque, those outer fibers, you can see that we're going to have a skewing of that rectangular section. We are not changing the length. We are now twisting about itself. This formula is a little bit different. This normal stress, average. It is average. It doesn't matter where I look along this cross section. It all is just P over A. Shear stress, torque. Torque is the internal torque at that point where we've cut it. J, much like A, is a constant for that cross section. You have to know what J is, polar moment of inertia. And then you have to recognize that this is for a solid and this is for a hollow tube. Or maybe it's the sleeve around something. Outer, inner. You also have to recognize that C equals the radius. C equals the outer, okay, the radius. Here we have the outer radius. Here we have the inner radius. It is not C naught minus C initial all to the fourth. It is C to the fourth minus C to the fourth. J, polar moment of inertia. Okay? So it is just standard for a cross section. Rho. I think of rho, I think of radial length. So rho is a distance along the radius. If I have, I'm going to erase this little guy right here now. If I have a cross section that I'm looking at and I have an applied torque, okay, I can see that if I'm right here at the center, there will be no shear stress because the fibers are trying to stretch around to stay together. So the farther I move along this radial line, the larger my torque becomes. So when our radius is 0, We don't have shear stress. As we move along the radial line, row, we get to the outside fiber. The outside fiber then is C. C equals radius. C equals radius, okay? So our shear stress that develops is radial, okay? It is a function of where you are along the radius. Much like we had with normal stress, we have a relationship between the shear stress caused by my external forces, and I end up with an internal resisting torque, okay? I am going to have some amount of strain, shear strain. I'm going to have some amount of skewing of that rectangle, if you will. G. G is my shear modulus of rigidity. Shear modulus of rigidity. It again is that value in my linear region of whatever diagram I have that's a function of shear stress and shear strain. It is that skewing of my little tiny square, okay? This is G. G is the slope of the line in my elastic region. So I have stress, I have material property, I have deformation. If I put a force which causes stress on a rubber band and I get a deformation, okay, that strain is going to be much, much larger than if I have the same diameter of steel and I put a force on it which causes the same stress that I had on the rubber band, but this time my deformation is going to be much, much smaller, because they may have the same stress, which is just a function of load and area, but their deformation is a function of the material that we have. Okay, so we could kind of look at that as I have stress, I have strain, and I might have something that has a very steep here, a very steep slope, and that's going to have an E. I might have something that has a very flat slope, okay? So when I look at this point of stress, whoop, we have to go way down here. When I look at this point of stress, I can see for my steel, I might have a very, very small strain, but for my rubber band, it's ginormous, okay? So this might be steel, this might be rubber band. They'd probably be a whole lot different looking than that, but it gives you the right idea. So the same holds true for here. If I have two materials, if they have a different modulus of rigidity, I can have the same stress, but I'll have a different amount of shear strain, okay? Much like we had the change in length delta, which is associated with normal stress, we have phi. This is my angle of rotation. It is a function of the internal torque and J and the length and G. Okay, so again, remember, T is that internal torque, L is the length, J is my polar moment of inertia, which is a function of my radius, and G is my shear modulus of rigidity, and it is going to be what kind of dictates how much angle of twist that I have. Okay, where does that torque come from? Normally it's in a powered situation, so you need to be able to go from a power, which is in horsepower potentially, and you need to be able to get that into torque, because the units we use are foot, pound, second. Okay, we don't use HP. You don't see that. You see foot, you see pound, and you see second. So every unit that you use needs to be foot, pound, second. And then we can convert this to inches, because that's actually what we need to work in, because stress yielding is KSI, shear stress is KSI, so we need to make sure we have correct units. These two equations have to do with thin walled. I need to recognize this is for a thin wall. It is not for a thick tube. It is for a very thin wall. Think of the things you might see on an airplane as you're walking in, and it's a very, an airplane is a very, 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 very thin walled structure. Okay, as we're pulling off down here, we need to make sure that we are recognizing what is shear and what is not. Okay, if you have questions, please let me know.